Not only can triangles be similar, all polygons can be. So let's just take a quick look at what I mean by a polygon. And the definition is basically a polygon is a many-sided shape. And so we've been looking at polygons with three sides. Those are called triangles. And there's a few different kinds of triangles. There's ones that have all sides that are different. Those are called scalene. There's some that have two sides that are the same and one that's different. Those are isosceles. And there's triangles that have all sides the same, and those are called equilateral. And we've been dealing with these three-sided polygons as similar figures. We haven't encountered the word scalene, isosceles, and equilateral too much this year, but in past years, hopefully, you do recognize some of that vocabulary. We can also have polygons that have four sides. And there's quite a few different shapes that we can have. So you can have a four-sided shape called a trapezoid, and it looks a little bit like this. Two sides that are parallel to each other and a couple of other sides. We can have a shape called a kite, and a kite kind of looks, some people call them diamonds, or I think they actually look like kites that fly up in the sky, so kites. If you combine some of the properties of both of those things together, you end up getting some more complicated shapes. If, for instance, you take trapezoids that have opposite sides that are parallel, and you also make these sides parallel to each other, you end up with an object called a parallelogram. And if you take a parallelogram and start to do things like make the corners all the same, 90 degrees, you end up with what's called a rectangle. If you take a rectangle and you make all the side lengths the same length, you end up with a square. And if you combine a parallelogram and a square, so you've got a parallelogram but all the sides are the same length, then you get something called a rhombus. And there's actually some interesting connections between here and here as well, which we'll take a look at if we get some time when we do some more geometry. There's also polygons that have more than more than four sides. So there's ones that have 5 sides and 6 sides and 7 sides, 8 sides, etc. I'll just give you the names of some of these. So this is a pentagon, hexagon, a septagon, 8-sided is an octagon, nonagon, a decagon for 10, and then a dodecagon for 12. So sometimes you'll see some of these objects. We now have some proper names for them. And any of these polygon shapes can be scale factored smaller and larger. We can use the idea of reduction and enlargement to alter these shapes. As long as the angles are the same inside and the shapes are similar to each other, they're undergoing these enlargements and reductions, we can basically use some of the ideas that we did with similar triangles and scale factors to figure out some missing sides to them. So let's put that together in the next little bit. By recalling that similarity, and the little symbol was that little squiggle, similarity means that all angles of our triangles were equal, so all the polygon angles will equal, and all the sides will be in ratio. When I say all angles are equal, I really mean all corresponding angles are equal. And when I say all sides are equal, I really mean, or all sides are in ratio, I really mean all corresponding sides are in ratio. So again, the in ratio part means the scale factor between the ones that are in the same place, that's what corresponding means, are equivalent. So if you've got an example of some strange shape, so here we go, here's it kind of looks like a house. This is actually a 5-sided shape, so it's a type of pentagon, and then I've got another pentagon, maybe it's a little bit larger, but it's that same shape. And in fact, if I call this one A, B, C, D, E, and so this one is maybe Q, R, S, T, U, I could say that A, B, C, D, E as a pentagon is similar to Q, R, S, T, U as a pentagon. And now when I start to put numbers in, like say this is 5 and 6, then I can start to put some numbers on the other one. Maybe this one is 15. And I can see the scale factor between here and here is 3, or I can go and write those same statements, like the side A to B is corresponding to the side Q to R, A to B and Q to R are corresponding, as is B to C and R to S. So BC and RS, and I could say, well, A to B was 5, and QR was 15, so there's that scale factor. Kind of the idea coming in here, and then BC was 6 and X for the RS, and I can use cross multiplication to solve this, or equivalent fractions to solve this, and I can reasonably quickly get an answer for my X value. I'd much rather that you use this approach, as it'll be more useful when these numbers suddenly become a little bit more complicated, to use this approach, because you'll just be, substituting in some things here and solving this a little bit differently. I know it's tempting to just go, oh, this multiplies by 3 and this multiplies by 3, but if the scale factor, if that enlargement in this case isn't as obvious, then you'll maybe get a little bit more stuck on solving these things. So, and it's also similar angles. So if I tell you that this one's 110 and I ask you how big this one is, well, that angle at the top between A, E, and D, so that's A to E to D, that angle between A, E, and D corresponds to the angle between Q and U. Notice they're the same letters, Q and U and T. So if I asked you what that one is, you could say it's 110 degrees because it's in a corresponding spot to the angle in ABCDE. But you do need to be careful, because sometimes the pictures aren't drawn in the right orientation. So as soon as one of these houses is on its side, or it's flipped around, if I took this and I said this is T and this is Q and this is S and this is R, and I gave you some more information, maybe this side over here is 7, suddenly the question becomes a totally different question, because it's not the 5 that's with the 15, it's actually the 7 and the 15. So you do have to look at the question and at the similarity statement as well. But as you can see, this is very similar to working with the triangles, so I don't think I need to show you too many more examples, and we'll play around with this in class. See you then.